Okay, so I'm sitting here sketching. Actually, I'm trying to learn Blender, and I'm sketching from a painting by Peter de Hoog. As usual, I'm trying to figure out the proportions and see if I get any bright ideas from the architecture and stuff. So I usually try to recreate the environment in the 3D program that I'm using. And right now, as I said, I'm trying to teach myself Blender. Before, I've used Maya and SketchUp and various software like Vue and Terrayen, and well, this seems much better. So I'm going to try to transition to Blender, and I've started by projecting the parts of the painting here as textures on the 3D geometry, and if I fade the original image out, you can see a test image that I'm currently working on, and I've added an HDR background, and I'm trying out different light sources and stuff, and put a couple of figures here from another painting, actually, just testing it out. And I'm really impressed by the real-time renderer in Blender 2.8. Really impressive. But anyway, I was struck by a peculiar feature here. When I click on the camera, I can choose a background image, and that's what I'm using here for reference with the original painting. But when I scroll down, I find these composition guides. That's interesting, but because that's something I usually put in myself to get a grip on the composition of the image. So here's the obvious things like center, and that you can't probably see it here, but it's a center line going here, and then center diagonal. That's self-explanatory as well. Thirds, it divides it into 3 parts. Maybe you can see it better if I click this on and off. Well, interesting. And the golden ratio. So what that basically does, it divides the format here, the rectangle, into the divine proportions, as they're called, or the golden mean, or the golden ratio, which is found all over nature, and has been a compositional guide for artists for centuries. Okay, so let's imagine we're going to divide this rectangle according to the golden ratio. We have a point here, A, and we have a point here called B, and then we have C over here. So we're talking about this hole and this, and of course this line here. So if we are going to split this, the height here, the length of the side, according to the golden ratio, we want to do it at the place where this shorter length divided by the longer is equal to the longer side divided by the whole. Okay. Let's go back to Blender. Okay, so they've done that here. You see the whole length there, and then also from the top down here. And where they intersect are often points of interest in a painting. You can see that very much in Renaissance paintings and Baroque paintings. And let's have a look at this one here. All right, so here are these points. We can see for a start that the opening here into the small corridor is aligned with the golden ratio here. What more? Well, we can see that the opening in the back also fits inside here, and very common in this in paintings from this time period. There's something happening either in this part or here or here or here. In this case, it's the woman here, and her gaze down at the kid, which follows the diagonal also from bottom to top here. And if we also project the golden spiral here, which just follows these lines. You see this starts down here, goes up, hits here, and goes down. Well, it spirals down into the center of attention. But I noticed something a bit strange, or I mean, it's not strange, it's just that I haven't thought of it before. Let's see. The golden ratio is projected, and then we'll project also the golden triangle A. Okay, so that projects a line that goes from here, and it hits the diagonal at 90 degrees. Let's see if I have a better... Okay, so here's the original image, and here's the golden cross, and here's a diagonal that goes from the bottom right corner through this golden intersection, and it hits the golden ratio here on the height axis. And I've seen that before. I hadn't seen this one before. Or I had, but I hadn't thought about it. If we compare it to the diagonal going here on the other side, it's apparent that this line was chosen because it intersects this line at 90 degrees. But this golden line here doesn't. It may look like it. It may look like this is 90 degrees, but it's actually not. It's something, when I measured it, it's something like 93 or something. But the one that intersects the diagonal at exactly 90 degrees, it hits somewhere else. So what would the proportions be of a rectangle where this red line would intersect here in the golden intersection here and hit the golden ratio on the height axis and still hit this diagonal at 90 degrees? Well, I know this is nerdy, but hey. So if we go to this one, this is the same line. It's, here are the proportions. So it's a line going there. Okay, it's the same. So I tried to adjust the angle there until it looked like 90 degrees. And I tried to measure this to find out what would this kind of rectangle look like. And when I measured it, I measured the angle here and the angle here and tried to get as close to 90 degrees as I could. But this is a crude instrument, and but I wound up somewhere like this was like 38 degrees and this was something like 52. Okay, and this line here that I'm measuring against is the golden ratio on the width axis. Okay, so this here shorter piece here is 61.8% of the longer one. That's why. Okay. But since we know that, let's posit that this is 1. This has to be 0.618, okay? From there on, it's basic trigonometry, and we can calculate it. So, we open up a Trigonometry Calculator. Okay, so this is the inverse cosine of 0.618. Okay, calculate. Oh, 51.829. So this seems like an important number. 51.83. And we put that in here. Okay, so we know the angle now. 51 point. Okay. So then the other angle is 38.17. And we know B here, that's 0.6180. Okay. And there we got it. We got 48. So A here is 0.4858. Now we can draw it. So we'll make a line. Let's say it's 6180. Okay. And I'm doing that because then I can do another line, which is 10,000, which makes it easy. Okay. So this line is divided by the golden ratio. Okay. And then 4858 going down at the 90-degree angle. Okay, and then whoa, there's one triangle and there's the other. Okay, it's a start. Now, to get to where this intersects the line here, we'll just continue this. Okay, so let's do this. We'll go to the according to the green here, and then we'll just continue this, and then we'll see where it lands. Okay, so this goes on here, there. This we can go all the way here. All right. Okay, so what we need to do is to divide this length from here to here, which is 7864.38 by the golden ratio to get the appropriate length here. Okay, let's do that. 7864.38 divided by 0.80, which is 12.72. Okay, let's just put it in here. Okay, 12.725. Oh, there we go. Okay, and then we can complete it. Okay, so there we go. Here it is. Now we have to check if it works. Let's measure it. Okay. This one we recently made. It's 12.725. And this one, of course, is 6180 plus 10,000. So 16,180. All right. So what's the dimensions? Okay, so 12725 over 16,180 equals 0.7864. I mean, interesting. Okay, let's draw it in Photoshop. So there we go. So if this side is 1, this side is 0.786. That is, this side is 78.6% of this one. And let's calculate 1 over 0.786, which is 1.2719. All right. And I guess we can round that down a bit to 1.727. Okay. That's nice. I usually make my rectangles 1 to 1.14. I like it. Looks good. And let's draw a line. From the bottom through this, hitting this. Now this should be hitting this diagonal at 90 degrees. Sure looks like it. Okay, but what is so familiar about this? 0.786. And also, what is so familiar about this? 1.2719. What is the significance of this number? Oh well, it's just the correlation between Earth and the Moon here, 1.272. It seems to have quite a close connection with the golden ratio, of course, since we built the rectangle out of it, and I'm sure there's a very easy explanation that could be presented by someone who actually knows mathematics and geometry, which I certainly do not. But this is fascinating. It seems that what we found here is actually the square root of phi. Now this is really interesting. The square root of phi is 1.272. So we can actually make this rectangle look a bit more fancy here. So instead of calling the sides here 1 and 0.786, we can simplify it quite a bit. let's just call them 1 and the square root of phi, and the proportions, the square root of phi to 1, which is still the same here. That's nice. Okay, to sum it up, apparently the only rectangle to have a diagonal crossing this is the intersection of the golden ratio, all the while also intersecting the diagonal at 90 degrees, is a rectangle based on the proportions of the square root of phi to 1. Wow. But wait, there's more. Some of the other numbers that figured in the calculation pops up in different places as well. Look at this. When the basic phi relationships are used to create the right triangle, it forms the dimensions of the Great Pyramids of Egypt with the geometry shown below, creating an angle of 51.83 degrees, the cosine of which is phi. Well, 51.83. That was exactly what we used here to get to where we got. That was the basis for our rectangle. Well, in fact, it seems like what we have created is a rectangle that has exactly twice the area of a triangle with the sides 1 to the square root of phi to phi. That is 1 to 1.272 to 1.618. And well, this is what's called a Kepler triangle. The mathematician and astronomer Johannes Kepler demonstrated this concept in the 17th century. Well, he said that geometry has two great treasures. One is the theorem of Pythagoras, the other, the division of a line into extreme and mean ratio. The first we may compare to a mass of gold. The second we may call a precious jewel.